Assalamu alaikum, and here we are back again for the next part of logistic regression. And today I'm going to be talking about gradient descent and how the parameters of logistic regression are computed or learned. Okay. So let me share my screen. Okay. So I hope you can see my screen now. Uh, Today's topic is going to be gradient descent. See? So, what is gradient descent? It's a simple algorithm for searching and exploring some space. So, this is an algorithm to explore the space of parameters. ठीक है? For a function or of a function. And what do I mean by this? Let me show it to you in drawing. So let's say I have a function and I'm going to draw the axes first. Um, let's say I have a function that's convex like this. And we need to make sure that our functions are convex, otherwise we are not going to get to what we want. So what we have on the y-axis is the cost function, and let's call it j. That's what we called it in the last class. And let's say, okay, we're looking at the parameter w, and since I'm drawing it in two dimensions, I'm going to say, okay, let's say there is exactly one parameter for the sake of discussion at the moment. See, so I want to find the best value of w, which means where j is being minimized. So this is the optimal value of w that I would like to have. See, so this is w at the minimum value, not the minimum value of w, but the minimizing value of w that minimizes j. So how do we do this? So we randomly select some w. So let's say we give it some random value, and let's say it falls here. So we give some random value to w, and it turns out, okay, when we compute the loss function at that value, this is where it falls. Okay? So what we are going to do is to calculate the gradient of j. So we calculate the gradient of j at this point. Let me I have my ruler. So let's say I calculate the gradient at this point, and this is what the gradient tells me, right? So what I do, since it's a convex function, I know, okay, the slope is this way, and I need to move in this direction. So I need to move in this direction, and I'll get a smaller j, and that's for sure because this is a convex function. So I'll move a bit. I'll so this is the direction I'm getting. I'll move a bit and get to this point. I'll compute j once again at this point. Okay, this is where I've moved the value of w, and what should I do next? So I do the same thing once again. I calculate the gradient here. It is, let's say, less steeper now, and I see, okay, the gradient is less steeper, but I still need to move in this direction. So I'll move further in this direction until I get to a point where it says, okay, the gradient is now 0. Okay? So the gradient is 0 here. That means I've reached the bottom of the curve, and this is where I want it to be. But sometimes it would happen कि you're here, you're jumping, you jump off here, you get the gradient in this direction, you move off here, then you get the gradient in this direction, and this keeps happening. So we need to stop at some point. Okay? We might not always get to the exact bottom, but we'll get pretty close if we run for a long enough time. Okay? So this is what the general idea behind the algorithm is of gradient descent. So let me write down this algorithm in pseudocode. So gradient descent. So step one, randomly select a value for parameter w. A value for parameter w. Okay. In the second step, we compute the gradient of our cost function j uh, at this, let's say, w. Let's call it w value, and we calculate the gradient of this cost function at this particular value. So then we move one step in the direction of the side where the gradient is less steeper. Okay? So that's what we were doing. And in this case, we are essentially updating the value of v to a new value. See? And then in the fourth step, we repeat until gradient is equal to, लिखना चाहिए या very close to 0. So yeah, so this is the algorithm, and this is what we'll be trying to do. Okay? And this brings us to the step size. Okay, when I said one step, what would one step mean? Right? And that's related to learning rate. So right now I was looking at just one parameter, and let's keep looking at that. So let's say it's parameter w. We have its value at time t, and we want its new value at time t plus 1. So time step t plus 1, we want a new value. How would we update that value? So that value would be updated by subtracting, let's say, subtracting this parameter multiplied by the uh, differential, sorry, of the cost function j in terms of which applies on x given w as the parameter. See? So in this case, this eta is going to be our learning rate. If it's going to be a high value, they're going to be bigger jumps. If it's going to be a small value, they're going to be smaller jumps. Uh, So a high learning rate means bigger steps. A lower learning rate means smaller steps. That would also mean that if we have lower learning rate, it's going to take more time steps to converge. On the other hand, if we have a very high learning rate, we might overjump the optimal point and keep jumping around the optimal, and that might not take us very close to the optimal. ठीक है. So now we want to extend our gradient descent to n dimensions. So for n dimensions, right now we have taken a look at it from one dimension perspective. So extending it to n dimensions, this requires the computation of gradient over a vector. So let me write this down. Requires vector calculus or matrix calculus. Computing the gradient for a vector function rather than a scalar. So what does that mean? So that simply means that we are computing the differential of, let me keep it as j. So this j, sorry, over some function that takes x and the parameters, and this would be a vector here in this case, w, given a vector y or a value y, sorry, would be equal to the differential with respect to, let's say, w1, the first weight, j of f of x given wp, the entire thing, and y. And then the differential with respect to the second weight, and all the way to n weights if we have n weights. Okay? So this would be a vector of differentials. Thus, we have this new vector wb at time t plus 1, and this would be equal to this is the update equation, wb at time t minus eta, the learning rate, and this is the vector differential of for j f of x w b for y, right? Which are the true labels, right? So how would we apply gradient descent for logistic regression? If you recall, okay, our loss function in logistic regression, the cross entropy loss, uh, given the weight vector w and the bias b, was equal to minus y log of sigmoid of wx plus b plus 1 minus y log of wx. This is the dot product plus p. Okay. Sorry. No, I did this wrong. So this is 1 minus log of wx plus b. Now this is correct. ठीक है? So it turns out I'm not going to go into the gradient details right now. So it turns out the differential of uh, this function, this loss function, with respect to gradient or with respect to wi, is going to be the sigmoid of w x plus b minus y multiplied by the x of I. So the value, this is the difference between an estimated y hat and the true y hat multiplied by x of I. Okay? The value of that particular feature of the document. Okay? So this means, okay, the cost function that we were looking at, g of wb, is equal to 1 over m minus 1 over m, and I'm going to just copy it over from the last lecture. This is sorry, this is 1 over n, and that's what we had last time. So summation over I going from 1 to n, and this is y of I log of the sigmoid of w multiplied by the ith sample, the vector for the ith sample, plus b, uh, and that's plus 1 minus y I, and I messed it up the last time as well. Okay, so this is this above 1 minus log of the sigmoid. So this again is 1 minus the log of the sigmoid. Let me write it down in the next line in this case right now. So this is the log of 1 minus the sigmoid of w x of I plus b. Okay, and what we wanted was the gradient for this. So the gradient for this, and you have to believe me on this one, of for the cost function is going to be the summation going from 1 to n, and this is fairly simple. This is the weight vector w and the feature vector for the ith sample plus b minus y of this is the true label, and this thing multiplied by the feature sample for the ith label. So this I is different from this I. Okay, so now we have our cost function, and we have the differential. So we can now look at how does this apply to gradient descent for logistic regression. Right? Let me give you an example. It has been a while. So let's take an example. It's not going to be any easier, but let's take it. So let's say, okay, I have this piece of text. It's again a review. Says good food, excellent service, uh, let's say nice weather, sorry, bad chairs. It's a mixed review, and second rate tables. I'm just okay. And let's say for in this case, you have just two parameters, x1 and x2, and these are the count of the positive lexicon words, and this is the count of negative lexicon words. So yeah, so negative and positive words are all that we're looking at. So essentially, good, excellent, nice, all these add up into x1, and we have bad, we have second rate, all these add up to x2. See? So making this example simple, we have x1, the value of which is 3, x2, x2, the value of which is 2. See? Now, if you recall, we need the weight vector w. So essentially, what we want uh, are w1, w2. We don't have these values, and we need a b. See? For our logistic regression classifier. These are the values that we need to train. So how do we go about doing this using gradient descent? So if you remember, what's going to happen is that we have a three-dimensional space. We have J, we have we have four dimensions. So we have W1, W2, and the fourth dimension would be B. And we have a function. So we have created J in such a way that it's going to be a convex function, and we are trying on, and this in this four-dimensional space, this would be a convex cup, and we are trying to get to the minimum value of uh, this cost function J. Okay. So how would we go about doing that for this case? So initially, let's assume we want some random values. So assume initial weights and bias. Let's say actually this does not really happen, are set to 0. Let's say this is the initial configuration. So we say okay, w1 is equal to w2 is equal to b is equal to 0. So we take these as 0, and then we take our learning rate eta to be 0.1. Let's say. Okay? So essentially what I'm saying here is that this vector of wb is 0, all zeros. Right? So this is what we have. And let's say this is the initial value. So I'm going to superscript it with a 1. So what would happen in the next step? So the single step update would require gradient computation, requires gradient computation, because in the next step what we are going to have is w and b at time t plus 1. Sorry, let's not do it time t plus, let's do it 2. So that would be w and b at time step 1 minus the learning rate, uh, and we need our j, ouch. So this is f of x of I given wb and y of I for that particular sample. So in this case, there's x of I. This would be our x of I, and the y of I would be the true label. So let's say we have some true label saying this is a positive. So y of I would be equal to 1. Okay? But what we need is the gradient. So let me just write it down. And so we need to compute this gradient j with respect to w, all the w's. So this is going to be d of dw1 the cross entropy loss with given WB, and again TW2, and the same thing, and dB, the cross entropy loss. This is the vector that we need to compute. If you recall, the gradient we computed for this was sigmoid of Wx dot product plus B minus Y, and this thing multiplied by x of 1. Then the next would be the sigmoid of W dot product with x plus b minus y multiplied by x2, and this would be wx plus b minus y and multiplied by 1, so I'll just leave it at that. So this is the vector that we want, and it would turn out, okay, since y is a 1 and these values of all the w's we initially picked are 0, so the weight vector and bias was 0, so this would become sigmoid of 0 minus 1 multiplied by x1, sigmoid of 0 minus 1 uh, multiplied by x2. This would be sigmoid of 0 minus 1 multiplied by nothing. So that's a 1. So this is what we have. And let's simplify this. Sigmoid of 0 is 0.5, because this is how the sigmoid functions looks like. It crosses the y-axis at 0.5. So the value is going to be 0.5 minus 1 minus 0.5 x1. The second one would also be minus 0.5 x2, and the third would be minus 0.5. Right? This is the vector we're getting. We know the values of x1 and x2 were 2, so 3 and 2. So this becomes minus 1.5. This is minus 1.0, and this is minus 0.5. So this is uh, the gradient that we get. And so now we have the gradient. So now we have the gradient of J computed as minus 1.5, minus 1.0, and minus 0.5. Okay. So what we have is the update equation, the weight vector and bias at time t plus 1 is equal to the weight vector, the bias at time t minus eta multiplied by this. And let's just plug this in to figure out the new values. So W1, W2, let me just formalize this. This is going to be W1, W2 bias at time t plus 1. This is going to be W1, W2 bias at time t minus eta multiplied by minus 1.5, minus 1.0, and minus 0.5. See? So this would be 0, 0, 0, right? And minus eta's value was the learning rate. We picked it at 0.1, and we multiplied by 1.5 minus 1.0 minus 0.5, and this becomes this becomes 0.15, 0.1, and 0.05. See, so these are the new weights W1, W2, and B at time t plus 1. See? So after one step, this is what has happened. So after one step of gradient descent, the weights have shifted only a bit though. ठीक है? तो W1 became 0.15 from a 0, W2 became 0.1 from a 0, B became 0.05 from a 0. Okay? And we repeat this. So we repeat the above steps until convergence. That is, the values of W and B are not changing significantly. See? So that's what convergence would mean. And lastly, and just going to say this, if we compare logistic regression to naive Bayes, so naive Bayes actually discounts, or it does not really discount highly correlated features. It continuously adds them, and the features that are reoccurring, it overestimates the evidence. So that's naive Bayes. Whereas logistic regression discounts the highly correlated features. See, so that's the positive of logistic regression. One of the negatives, or some of the negatives of logistic regression, is that logistic regressors require large data sets to be trained, and secondly, they take a lot of time to implement and train as well, unless you're using libraries. So training times are high for logistic regressors, as you will see down the line when we are training neural networks. Okay, so that's it for gradient descent, and thank you very much for listening. I hope this helps you down the line, and definitely will. If you have any questions, you may ask now.